Srinivas sir is joining now. And you send the joining link today. Link you send. Hello, Manjula.
Yes, ma'am.
Yeah,
Yes,
recording
ma'am.
also you have to start. Recording also you have to.
Oh.
You have to start recording also.
Oh, okay, ma'am.
People are joining. 5 minutes we will wait. And Srinivas sir, I have sent the link. So,
Yeah, I just joined.
oh,
I will
good
share
morning,
the
sir.
screen. Hello, good morning.
Yeah, good morning, sir. Just 2 minutes we will wait.
Yeah, no
It
problem.
started 10. People are joining. Hello, Manjula ma'am. Now control is in your hand, na?
It is the organizer is Chenappa sir, ma'am.
No, he
Sir
has
is
given you the credential.
okay.
Or else you tell him, WhatsApp him. He told I
Yeah,
am
yeah.
giving the credential.
I have informed him, ma'am, to start with the recording.
Yeah.
Ah.
I think you can start formally till people will join. Because sir has joined.
So, are you able to see the screen? My slides.
Uh,
I will also send you
no,
so
sir.
that if there's any problem, you can launch from there.
Okay. But now screen is not visible, sir.
Yeah, just a minute. I will do that also.
Manjula ma'am, you have to take the screenshot also.
Okay, ma'am.
So I have sent you the slides. If there's any problem loading from here, we can use that.
I got the slides. I am trying to. And Manjula, I am sending you also. See, Manjula ma'am, you got?
Ah.
Yeah.
Yeah, I got
down-
yours, ma'am. PDF.
Download. That only. Download. When I got, I am trying to share. I am trying to share. Yeah, net is very slow. Can you share, Manjula?
Yes, ma'am.
Okay, share it. You are sharing, Manjula ma'am?
Yeah, I will do it. Visible now,
It's
ma'am?
coming. It's coming. So let it be like this now.
Okay.
You can start the formal introduction then. Sir, it is visible to you, sir? Srinivas, sir? Hello? Srinivas, sir? Okay, formal introduction you can read,
Hello.
Manjula ma'am.
Okay, ma'am. Is
You're
my
able to
voice
hear me now?
audible, ma'am?
Sir, we can see you also, sir.
Are you able to hear?
Yes, I can able to hear also.
Yeah. Then we see in the beginning it may be slow, the slides, but later on we should be quite fast. Okay.
Okay. So now we will
Okay.
start, sir, formal introduction.
Yeah, let us continue with this. And make it
Okay.
full screen.
So you are
Okay,
sharing
sir.
or Manjula? Who is sharing?
Now,
Sir,
So I'm not
sir,
sharing.
actually Manjula is sharing.
Okay. Shall I share
yeah.
or not necessary?
Manjula, you will
Should I
share,
share or not necessary?
Yes.
No,
Anything is fine, ma'am.
Let me just try once
it-
again. If it works, then we'll go. Otherwise, we will continue with your slides.
Okay, sir.
Just a minute. I will also share.
It is visible to us, sir.
Yeah, I'll make full screen. Is it appearing full screen?
Yes.
Hello.
It's appearing full screen, sir.
Okay. Then this, what is it called? Your video. Yes. Yeah, we can start.
Let me start, ma'am.
Yes, sir. Yes, ma'am.
Good morning and one.
So I'll take
Good
1 hour.
morning, one
Or
and
how
all.
long can I go? How long can I go?
Yeah, 1 hour, sir. 1 hour.
Okay. Okay. Yeah, please continue.
Good morning, one and all, and welcome to the 4th day of 15-day faculty development program on quantum computing and sensor technologies. Ladies and gentlemen, esteemed colleagues, and distinguished guests, it is with great pleasure and honor that I stand before you today to extend a warm welcome to our esteemed guest, Dr. Srinivas Talabattula, sir, professor in the Department of Electrical and Communication Engineering in the Department of Electrical and Communication Engineering at the prestigious Indian Institute of Science, Bangalore. Dr. Srinivas' journey in academia and research is nothing short of inspiring. With a foundation laid upon physics honors from New Science College, Hyderabad, followed by an ME integrated and PhD from the esteemed IISC, he has exemplified dedication and scholarly excellence. His academic prowess was further honed during his tenure as a postdoctoral research fellow at Toyosha University of Technology, Japan, where he immersed himself in the intricacies of optical communications with a particular focus on photonic integrated circuits. Dr. Srinivasa's contribution to the field of optical communication are extensive and profound, evidenced by his impressive publication record comprising approximately 150 papers and his mentorship of 28 PhD students. His commitment to academic excellence extends beyond research as he actively engages in shaping the future of engineering education as a member of the National Board of Accreditation. Beyond his scholarly endeavors, Dr. Srinivas is a beacon of leadership within the academic community. His tenure as the chairman of GATE IISC Zone and his roles within the IEEE Bangalore section, including his chairmanship of both the IEEE Photonics Society and IEEE Communication Society chapters, underscores his commitment to advancing the field and nurturing the next generation of engineers. Dr. Srinivas' dedication to fostering collaboration and knowledge sharing is evident through his extensive engagement in technical talks with over 100 delivered at various institutions across the country. His efforts have been instrumental in the formation of numerous student branches and society chapters within the Bangalore section, further enriching the academic landscape and fostering a culture of innovation. Please join me in welcoming Dr. Srinivas, sir. Thank you. Over to
Thank you very
Srinivas,
much.
sir.
Yeah, thank you very much. Let us get started. I will take about 1 hour. Of course, there are a lot of slides, but we'll have a lot of discussion in the end, I suppose. So this subject, first of all, let me thank the organizers for inviting me to give this talk, and I'm very happy to participate. I would like to just ask them to let me know a few one or two sentences about this FDP that is going on. Did you already have quantum communications and computing talks in this series already? Dr. Preeta Sharan?
Yes, yes,
Hello.
sir. We are
You already
having.
had?
Yeah.
No. Did you already finish some earlier in all these 4 days? Did anyone talk about quantum already?
This one in my previous FDP 1 week before which we have finished. Dr.
No, not
Gaurav
in the
Bharti.
previous FDP. In this audience, do they
in
already
this
have exposure to quantum?
no, today afternoon, one talk is there from Nirma
Hmm.
University, Ahmedabad. She is going to talk
Okay.
on the quantum today. First,
Oh, which aspect of the quantum will he speak?
she will
Is it
talk on the
basics or
quantum
no?
basic
Because
of
I
the
don't want
quantum.
to repeat. Excuse me.
She is going to talk on the quantum dot.
Okay, okay, that is different. Okay,
That is
okay. Let us talk about when we say quantum in the FDP. The keyword is there in the FDP. We assume it is quantum information, not quantum devices. I suppose some of you who are participating in this FDP have looked at web about what is quantum and so on. Little bit exposure, I suppose, at least in terms of the current developments. You must have read as a news at least. May not be fully technical, but I will assume that some of you have got some interest in quantum. And I hope you will realize that we are talking about quantum information technology, not quantum devices. What Dr. Preeta mentioned in the afternoon is the quantum devices. Quantum dots and all come under quantum devices. Okay, that we'll discuss if someone has doubts. For the time being, let us go with this topic called quantum information technology. It includes quantum communications, quantum computing, and so on. And in particular, I'll specify photonics as the route to quantum. Okay, as you know, this quantum information technology has become very popular now all over the world, as well as in India and in many colleges in Bangalore also, where faculty members and students are interested in quantum information technology. It promises many things which have not been done using classical. As we go along, I'll mention many of these. Okay. So before I go further, I will acknowledge my students who have worked on this subject further, and maybe I hope I'll be able to show you some little bit of work that we have been doing in this presentation also. So I will request other organizers, if there is any interruption in the network or if there is any problem, you can call me directly on the phone and we can set right. So this is a brief outline of my presentation. We'll start with a brief introduction to quantum information technology, a little bit about the history, and then we'll go on to the basics of what is qubits, what are quantum systems, quantum logic gates. Then we'll look at block diagrams of quantum computers, quantum communication links, and so on, and a little bit of work that we have been doing in our lab also. I hope that is all right. If there is any overlap or discrepancy, please let me know. So to start with, quantum information technology implies that we use the quantum states of these objects for communication and information purposes. We have the opposite of this is called the classical information technology, which we are all familiar with. The present day world that we are living can be called as a electronics era. So all the information technology is based on the electronics. Okay, that means the data or the information that we transmit is represented electronically. Okay, we have the VLSI circuits which create or generate all this information. If you have the information in the physical form, in the mathematical form, it can be translated onto physical form through electronic means. So zeros and ones are represented by currents and voltages. That's what is meant by the classical information technology. And sometimes in the recent times, you have the fiber optic communications where the information is represented in terms of light amplitudes and phase values. For example, 0 intensity corresponds to 0 bit, 1 intensity corresponds to 1 bit or 1 milliwatt or whatever you want to call it. And similarly, sometimes we use polarization. Horizontal polarization can represent 0 bit and vertical polarization of the light wave can represent 1 bit. So there are various ways to represent the information physically. But the most important thing is we use bulk devices or bulk objects to represent this information. For example, when you say 1 milliwatt of power or optical power or 1 milliampere of current, there are many electrons involved in that. Where the classical domain of classical information theory. When we are talking about the quantum information theory, we want to use the quantum properties of these objects. Many of you know that when you go to the atomic level, you encounter quantum phenomena. For example, the atoms or the photons, they have quantum properties. That means I will elaborate further later as we in the next slide or so. So we can say that classical information deals with classical objects of zeros and ones represented definitely by using these values. And quantum information, when we talk about, we are dealing with the objects with quantum properties. Okay. So similarly, a quantum computer means that we are using the quantum properties of the objects or the information to represent. Similarly, a quantum communication link will use quantum properties of the objects for communication. Now the keyword is quantum. Okay. So historically, Richard Feynman is accredited with a lot of quantum related tasks, including quantum information. He is the one who predicted, you can say, that you can build quantum computers, which means we can use quantum properties to build computers. And also, many people later on have shown that a lot of big problems can be solved by quantum computers rather than the classical computers. There are many problems that we cannot solve by classical computers. And mainly because of the power that is required. Very high computing power is needed. Sometimes it's not possible to solve at all by classical means. Okay. So this is a brief timeline of the development of quantum information technology. Starting with the Feynman's proposal of the idea of quantum computation, then you have one of the first, earliest quantum communication protocols called BB84. Then you have the development of a model of quantum computers. Then further, as we go along, you have several protocols for quantum communication computing. In particular, the idea of quantum entanglement. That means there are two objects which are correlated. Then you have the Shor's algorithm for factorizing very large numbers. You can easily think of some of these problems. If you want to factorize a large number, it takes very long time. Large number is sense thousands of digits. Okay, if it's a small one, we can do by hand, or if it is a reasonably small, reasonably big, we can use existing computers. But once the numbers become bigger and bigger, it's not possible to do using classical methods. Okay. Similarly, search algorithm. Big data is an important problem in the present day world. So Grover's search algorithm is one of the important events in the development of quantum information technology. Many people have developed a lot of models of quantum computers, quantum communication systems, and so on. So let me jump to the recent times. In 2016, the China has launched the first quantum communication satellite, MECS-1, and later on many developments. Nowadays, many companies like IBM, Intel, Google, etc., have their own R&D programs on quantum computing. So people predict that in the near future we'll be able to see the quantum computer, maybe about 10 years or something like that. So let us go to the basics. The basic idea in quantum information technology is the qubit. In classical world, we use bits to represent information. That is simply zeros and ones that we are familiar with. Now let us understand what is meant by a qubit. So in quantum world, we will use the quantum objects. Many of you know that electrons have got quantum properties. The spin of an electron, for example, the spin of an electron can be up or down. So it has got a quantum property. Similarly, a photon has got polarization, horizontal polarization or vertical polarization. But what is the main difference between the bit and qubit is the state of the object is not well defined. The object is in particular state which we are not able to express clearly. It's not well defined. Just a minute, please. So the main idea of a qubit is related to the representation, and its evaluation. So the state of the object is not well defined. For example, if you think of a photon polarization, it is very easy to visualize polarization. So I will use the example, and also I have mentioned that we will use photonics to um, explain many of the phenomena, represent phenomena. Importance of photonics is that the people have considered or come to a conclusion that photonics is the best way to build quantum computers. And of course, it implies that photonics is the best way to represent the qubits. So we'll use photon states to represent the qubits. So I can say the horizontal polarization is 0 qubit and vertical polarization is 1 qubit. But the crux of the problem is that the state of the photon is not well defined. So it can be at any angle. Compared to classical light waves, where we can say that we can clearly measure and say this is horizontal polarization, this vertical polarization. If a photon is given to us, we cannot exactly say that it has gotten horizontal or vertical polarization. But what can be said is the probability. We can say that the photon is in the horizontal polarization with so and so probability. We can say that the photon is in the vertical polarization with so and so probability. So the state of the photon or the polarization state of the photon has got a probability for every angle. Suppose horizontal polarization, when we say there is a distribution around that, it can be -1 degrees, -2 degrees, -3 degrees, etc., but with a different polarization. And we should talk, when we have the distribution function, we can talk about the mean, averages. So the PDF has got the average. So that is represented by what you are seeing there. This ket notation implies that the average of this photon is horizontal polarization. Similarly, when I say that ket1 is the vertical polarization state. So instead of talking about definite values, we are talking about the averages. We are talking about the PDFs and averages. That is the main difference between bits and qubits. So, and the representation also shows here this ket notation, 0 ket and 1 ket. So how do we determine this? PDFs is an important question, which I want to diverge right now for a short while. In the quantum world, you know that wave function represents all the properties. Suppose you say that an object is at a particular point x equal to 0, we mean that the average of that is at x equal to 0, and there's a PDF spread across x equal to 0. So the average is what we are talking about there. Similarly, if you want to, how do you get that position? You have to operate on the wave function. You have the displacement operator or the position operator, which operates on the wave function and gives the average of this. Similarly, if you want to find the momentum of the object, you operate the wave function with the momentum operator, and you get the average of that momentum. Similarly, all the statistical and random properties can be operated. So at this moment, we are talking about the state of the qubits. Their horizontal polarization or vertical polarization are represented by using the average of that PDF function rather than definite values. That is the most important thing that we should understand about the qubits. So how do you get that wave function? You should go back to the quantum physics and solve the Schrodinger's equation subject to all the environmental conditions like the potentials and so on to get the wave function. That's where we operate. So for the time being, you need not worry about the quantum physics, but imagine that the qubit state is represented by an average value of the various parameters, like average value of the position.
Sir, here only,
Yes.
because it is very interesting for me. So here only
Yes.
one question, sir. So how
Yeah, please.
photonics and quantum you are correlating? Like it's a average of that. Just horizontal is the 0, vertical polarization is 1.
Yes.
So
Yes.
can we say that polarization of the photon in horizontal is 0 and vertical is 1?
Yes.
And in quantum
Yes.
also, qubit we are representing 0 and 1. In this way we can correlate,
Yes.
sir?
Yes. Instead of saying horizontal polarization is 0, we will say average or the mean or the ket 0 is the 0 qubit.
Yes.
And ket 1 is the 1. And the actual photon can be in at any angle, but with different probabilities. And if you want to get that probability, we have to operate on the probability distribution function, which we can get by using quantum physics from Schrodinger. So instead of using zeros and ones, we are using ket 0 and ket 1. That is the main difference. And the actual state of the photon can be represented by the superposition of the 0 ket and 1 ket. The next line, when you see quantum superposition, the actual state of the photon can be anywhere between 0 or between 0 degrees and 360 degrees, which we can represent by using alpha into ket plus beta into ket 1. Okay. So the actual photon can be in any state. So what are these coefficients alpha and beta? They can be, because we say that psi is a wave function, it can be a complex function, not only a real valued function. So we are dealing with the complex wave function, including phase, amplitude, and all that. So the probability of getting 0 is this. You see, in quantum physics, you say that psi square is the probability, not psi. Psi is the wave function, psi square is the probability distribution function. So we should talk about alpha square and beta square. Alpha square will represent the probability of getting 0, and beta square is representing the probability of getting 1. And of course, the total probability has to be 1. So alpha square plus beta square is 1. So alpha and beta can be complex values. That is an important conclusion in quantum information theory. So the state of the photon can be a complex value. Okay, we have to write the, and how do you represent geometrically?
It should be only complex, or it should be real also.
It can be real also. Real is also a complex number. See, a specific case of complex number. For example, a plus ib, if you want to call it. If b is 0, then a is real, fully real.
Okay.
So complex numbers will include real numbers also. Because like integers are also included in real numbers. Fractions are included in real numbers. So all numbers are included in complex numbers. And there is no other bigger set than complex numbers. We don't need some other super complex numbers. Okay. And of course, there is also for those who are interested in mathematics, there is also the idea of tensors and all those things. Okay. So in the present day world, we have come to the conclusion that the numbers are complex numbers, nothing more than that. Okay. And we can represent, suppose you want to represent the quantum state of an object or a photon by geometrically, you see you have two variables, alpha and beta, and 0 ket and 1 ket can be called as the basis vectors. Even though we have not discussed, 0 ket and 1 ket then can be represented by matrices. For example, 0 1 can represent 0 ket and 1 0 can represent 1 ket. So we can also, instead of dealing with the continuous valued functions, we can deal with matrices. Okay, for the practical purpose in the quantum information theory, learning in terms of the matrices is very good. I'll show you as we go along with logic gates and all that. So psi is a linear combination of 0 ket and 1 ket through this alpha and beta. So if you want to plot this function psi, you will get a sphere. Okay, so the points, all the points on the sphere will belong to the states that are possible for psi. So the 0 can be one direction, 1 can be other direction, and a linear combination. So there are a lot of points. Like for example, 0 plus I, 0 ket plus I ket, 0 ket minus I ket. These are all the various possibilities for the state of photon. Okay, you can also represent it using the polar coordinates. Instead of rectangular coordinates, you can also use polar coordinates for alpha and beta, and you can visualize the qubit states. For a single qubit, this is very, very useful. But next, we don't deal only with single qubits. We need many, many qubits. Suppose you want to represent a lot of quantum information, we need to go for many, many qubits. So how do you get them? So you should have more number of photons. Suppose you take 2 photons. Then you have combinations 0 0 0 1 1 0 and 1 1. These are the combinations. and the probability distributions functions are there for the first photon and for the second photon. So you should combine these two and you get a joint probability distribution function, f of x comma y. X will represent the first qubit state, y will represent the second qubit state, and they can be correlated or independent and so on and so forth. All the possibilities are there. 0, 0 ket, 0, 1 ket, 1, 0 ket, and 1, 1 ket. This is a joint probability distribution function and the joint qubit states. So a 2 qubit system will have 4 qubit states. 0, 0, 0, 1, 1, 0, and 1, 1. Similarly, n qubit system will have 2 power n qubit states, or the basis vectors, 2 power n basis vectors are possible. So a linear combination of 0, 0 ket, 1, 0, 1 ket, 1, 0 ket, and 1, 1 ket will represent the composite state of a 2 qubit system. You observe that the number of qubits and the states for the photons is going exponentially. So if there are n objects, n photons, you have 2 power n possible qubit states, 2 power n possible basis vectors. Okay, so it is going exponentially. That means approximately people say, or if you go to the theory, you can say that a n bit or n qubit system is equivalent to 2 power n bit classical system. So if you're having a 16-bit computer, classical computer, you need only 4-bit quantum, 4-qubit quantum computer, something like that. And there is no pictorial representation. If the number of variables go more than 3, we cannot represent geometrically easily. Okay, but you can visualize. Okay. So let us get going. Now let us look at quantum gates. So you can look at quantum gates as system. Some of you would have come across control systems and so on. There are inputs and outputs. So input is some quantum state, output is another quantum state. So how do you relate them is an important question. For example, for a single qubit state, something is the input and something is the output. So qubit states are 0 ket and 1 ket. So you can have a matrix of 2 by 2. So there are X, capital Y, capital Z are different possible matrices for input qubits. So you can easily work out. Suppose if say 0 ket is 0, 1. Say I will, for the time being, I will represent 0 ket and 1 ket by matrices. 0, 1 is one matrix, 1, 0 is another column matrix. So you can multiply X with 0 ket and get what is the output state. For example, if you have 1, 0 as the ket for the 0 state, you have 0 and 1. That means it is not changing anything. X is identity. Okay. If you give a 0 ket, output is a 0 ket, or 0 qubit will become 0 qubit for the X. Similarly, you look at Y. So it is giving minus I and I. Is it not 0? And you can say the same thing, you can work out with 1, 0 also. So I have a little bit of workout we have done here for you. So this is the second line is called the Hadamard gate. If you have a
So, sir,
0 ket, yes.
Hello, sir. Sir,
Yes, yes.
in case of Y, it is the 1 ket. So 1 ket is represented by 0 minus I and 0. This is the 1 ket.
Not like that. You see, for example, I'll take 0 ket, 0 qubit state. So I'm representing by 0 and 1. So what is the output? Minus I and 0. When you multiply 1, 0, right hand side for the Y, let me say 0, 1. 0, 1 is minus 1 and 0. Minus I and 0, is it not? When you multiply, just a minute. When you multiply 0 minus I 0 with 0, 1, you are getting minus I 0. That is the output. Okay. There is no classical output corresponding to this transformation. Similarly, Z you take 1, 0 and 0, 1. And you also work out with the second qubit. What is happening to, you see, when you are talking about logic gates, you have to work for 0 and 1 both. We must make a table. Okay. Similarly, 1, 0 will give you 1 and -1. Is it not? 0 and -1. Z is giving 0 and -1 as the output. Let us look at Hadamard gate, which is shown below. So Hadamard gate is represented by 1, 1, 1 matrix, last this thing. So the output is 0 ket plus 1 ket and 0 ket minus 1 ket. There are two possible output states for the Hadamard gate. So 0 qubit is getting transformed into a superposition of 0 and 1 ket. So that is not possible in the classical logic gates. Okay. Some more examples I take as we go along. So we are using matrices to work out. It's easy to work out. Even if you don't understand fully the implication, you can easily work out the matrices. Now I'm looking at what is called the C0 gate. C0 gate has got two inputs, C ket and T ket. C and T are qubit states. C is called the control bit or control qubit, and T is the signal qubit. So what is the output of C0 gate? You can look at the matrix here. Actually, it has been worked out backwards. That's how this matrix comes. Okay, you look at what is 0 qubit at C, 1 qubit at C, and 0 qubit at T, and 1 qubit at C, and see what is that you want to get. So the function is decided like this. When C is 0 ket, we want to get T at the output. When C is 1 ket, you want to get not operation at this point, not of T. So if you look at the matrices, you can easily work out. So what is the input to this C0 gate? 0, 1, 0, 1, or x1, x2, x3, x4. These are all the possible states for the input. And you can easily see that this does not operation when C is 0 and flip of that. It pass through states when C is 1 or the opposite. Okay. Similarly, you can think this is the other pictorial way of representing the C0 gate. Similarly, there is also called what is called as double C0 gate, Toffoli gate, C1, C2, and T. These are three inputs. That you have a matrix with 8 values: x1, x2, x3, x4, x5, x6, x7, and x8, corresponding to different qubit states of the input. So you multiply and you see what you get. So double C0 is represented by this operation. When both C1 and C2 are 0, then the T is pass-through state. When C1 is both C1 and C2 are 1 qubit states, you get a NOT operation here. And all the combinations for C1, C2. Okay, you need not look at it as only C0 gate. It can represent many things. It is actually called a Toffoli gate. You can see, take these three as three inputs, C1, C2, C3, and then work out. And using series matrix, of course, is once again composed backwards. This is how you present. So I hope many of you have recognized that there are many quantum states which are not there in classical. In particular, if the quantum states can be imaginary, they can have imaginary representation. The matrices can be imaginary. Let us get going. So it is very easy to derive classical gates. You can have a quantum NAND gate by using the matrix properties. Similarly, you can have a fan out, quantum fan out. Suppose X is the given qubit, you can get X at the out as well as X at the second port also, which means this is a probability distribution function. It doesn't mean both are same. Okay, I hope everyone has understood that X, both outputs look X. Actually, it is not so. It is represented by the PDF of X, PDF of this. Two PDFs, two identical PDFs, because both are same. That means, suppose the photon can be in 0 state here and 30 degrees here, actual state. But you can say that both have the same PDFs, and so the same qubit state is at the output. We cannot divide the quantum objects. Photon, you cannot destroy. You cannot divide photon into two parts and then give one at the first input and second at the output. Unlike in a classical gates, you can say half the power in the first port, half the power in the second port. It is not possible to do like that. The same photon will appear either at the first port or second port, but with a different probability. You should think in terms of the probabilities if you want to understand all these classical gates. I hope you got the main point. Okay, please ask me questions if you are confused. Now let us go further, because we have spent enough time on the quantum gates. Let us go to there are what are called DiVincenzo criteria. If you want to build quantum information systems like quantum computers, then we should look at these properties. So we need a physical system with scalable properties. That means you should have many qubits. We should be able to characterize their qubits, their quantum properties, their PDFs, and so on and so forth. It should be available to us if you want to build a quantum computer. It's not an easy thing. Actually, one of the important things that you must have come to your mind is how do you generate these qubits? That is a physical problem. Like how do you generate a single photon? We need to generate a single photon or a single electron. People have done using many methods. In the next slide or so, I'll show you. I'll tell you. So we should have a scalable physical system with well-defined qubits. We should also have the ability to initialize the state of the qubits. So by passing through certain gates, you can say the input to the overall quantum computer is so and so. We should be able to characterize the initial states of the qubits. Then there is what is called the decoherence. If I have a qubit, if I leave it like that, it will reduce and its properties change. Horizontal polarization can become vertical polarization gradually, even though you don't do anything. Just in the physical system, in the vacuum also, if you put it, then the horizontal state will not remain horizontal state and vertical will not remain vertical state. This is not possible in the classical world. Yes, please. Yeah, hello. You have some question? Hello. I hope everyone is able to hear. Someone can reconfirm. Once in a while, I'll ask. Dr. Pritacharan, you are able to hear me?
Yes, sir,
it is
we are
audible.
able to hear.
Yeah, fine.
Yes, sir. Yes,
So
sir. We are
decoherence
able to hear.
means just randomly the state of the object, the state of the photon changes. In the classical world, it doesn't change. If you have 0 milliamperes at the output of a circuit, it remains 0 amperes forever in principle. Okay. So then we should have a universal set of quantum gates. Like in conventional electronics, you use NOT gate to build many complicated VLSI circuits. Similarly, we should have a universal set of quantum gates, like quantum NOT gate may work. It may not be the ideal one, but we should have a universal. For any given system, we can define a universal set of quantum gates and then work out. Like in electronics also, in the beginning days, you have PNP transistors, NPN transistors, and people have converged out to some particular type of gates to build the bigger and bigger systems. And then you should have a measurement capability. We should be able to say, even without measurement, that a certain output is so-and-so qubit state. That's what is meant by quantum capability. So you must also have an ability to convert from one state to the other state, even though we may not be able to say. See, in all these cases, please remember that we are not observing the qubit state. We cannot observe. Once you observe, it collapses to one of the states, either 0 ket or 1 ket, okay, with some probability. If you do another experiment, it may become something else also possible for the same system. I hope you understood that. And then also the last point is flying qubits, which means if you want to transmit qubits from one point to the other point, you call them flying qubits. That means due to the movement, the qubit properties will change. You should take care of those. Okay. So this is a broad, big picture of a quantum computer. If you want to build a quantum computer, you take a layered approach. See, I'm not this from now on. I will not be very exact, conceptual. Okay, I'm just showing you the diagram. I suppose until now, little bit conceptual we have discussed, and I hope you have understood many things. And now let us look at how a broad quantum computer looks like that. If you want to discuss exactly, we should go to the mathematics, which is given below. See, we can use the mathematical properties like matrices, random process, and so on to understand all these things accurately. I have lots of papers and books. If someone wants to go systematically, you can go through those and learn. I can also attend a lot of workshops and courses, online courses, etc., to understand this. But ultimately, we have to learn ourselves. See, the teacher or whoever is giving the video course, definitely yes, all the information is there correctly, but we may not be able to receive exactly. Our mind has to be ready to accept all these things properly. For that, I think we have to read books. Some standard book on quantum information theory is necessary. We should read ourselves and then understand, and then you go back to the video course or some other course to understand further. Without understanding anything ourselves, it's very difficult to go further. That's what my experience is in learning this quantum information theory. So let us get going. A quantum computer is thought in terms of the layered architecture. Like many of you are familiar with OSI model, 7-layer OSI model. If you want to understand the internet, you have to go through 7-layer model. Similarly, if you want to understand a quantum computer, we should go through these layers. So the most important points in the laser in these layers are mathematical model to start with, which is based on the quantum physics and all that. Then you should have a computational formulation. See, what is the computational function you want to achieve, like a general purpose mathematical operation and so on. So we should have a computational model for the same thing, next level. Then, like in the computer science, you should have a compilation model, compiler. You should have a quantum computer compiler, which can be further upgraded into software. These are the examples that are given below. Acronyms I don't remember, but you should convert it to a software model. And of course, finally, once again, you should go back to the physical system. The software has to be converted back into the, say, for in the I would suggest everyone to compare with the classical computers. If you're thinking about a quantum computer, think about the classical computer and how we do that. Finally, these are converted into physical states, like the memory states, like the registers, and so on and so forth. You must be familiar with. Okay, and the process repeats. The design, you don't do it in one go. You have to several iterations to do to get to a correct, good design of a quantum computer. Okay, so these are some examples that are taken here. For example, pair creation is what is shown here. Then the circuit model. Then the what is that, compiler states, and then the algorithm, and then the physical representation. In this case, he is using electrons states. So at intermediate point also he has shown a more elaborate block schematic of this move operation. Suppose you want to do inputs are A and B states. You see, you must have observed that NOT gate is used. C NOT gate is used to represent these, and also using inputs A and B gates. Okay. So further, the same thing is put in the form of design flow and abstract flow. So the design flow of a quantum computer design will consist of a quantum, start with a, see, like in the computer science, we start with the quantum program, you have a front end, then the technology dependent optimizer, then and so on and so forth. Several iterations have to be done. And of course, you can make a simulation also of, see, many times we are interested in, we may not be able to build a physical quantum computer. So there are a lot of quantum simulators available nowadays. On the classical computers also, approximate quantum computers could be simulated. Of course, finally, we would like to operate on the actual quantum computer. So there are a lot of tools available like IBM QS-Kit and so on, where you can operate, you can get a feel of these quantum operations on a classical devices. So let us go further. Let us look at what is meant by quantum communications. So point to point, we want to transmit information from one point to the other. Information represented in the quantum bits. Then you need physical transmitter and receiver consisting of a source, detector, and also you have the channel. You need a good channel to transmit, like the free space or fiber optic cable or whatever. And then there is a noise. There's a lot of different types of noise, like in the classical system, quantum noise is there. Then the physical, whatever the physical devices, like in the afternoon, you may be discussing about the quantum dots. They can also be used as a quantum devices to represent quantum information. Okay, that we'll not discuss right now. You please ask the speaker in the afternoon how quantum dots can be used for representing the quantum information. Okay, and we have discussed about this currents and voltages. The other point I have put here, many times people are using polarization state of the photons. You can also use the angular momentum of the photon to represent qubit states. Channels also have got their own properties. You must contrast between the classical properties of the channel and quantum properties of the channel. Like the free space is a useful thing. And you see, many times you feel that we are using electromagnetic waves to transmit information from one point to the other. In classical communication also we use electromagnetic waves. But the space itself is the channel. Similarly, people have thought about gravitational waves to transmit information, both quantum information as well as classical information. But I think gravitational waves are being used in the extraterrestrial systems to communicate between galaxies, pulsars, and all those things. People feel that we are getting quantum information from all these galaxies. We are not able to receive accurately because we don't have good quantum devices on the Earth. Okay. I suppose a lot of quantum communication is going on in the universe. An important idea in quantum information theory is the entanglement. You can generate two photons with correlated properties. You can imagine coin tossing experiment. Suppose I toss a coin, I'll get head or tails. I'll toss a separate coin, I'll get head or tails. Suppose I join these two coins in some simple way using some thin wire or rod. Then what happens if you toss? You can toss both together and get both head or both tails. This is only an example or a model. So you can generate two photons with correlated properties. That is what is called the entanglement. So if the first photon has got a cat head, you can say that second also has got cat head. So the probability distributions of the two photons can be same. Okay. In the beginning, when we talked about two photon systems, two qubit systems, we did not consider this property. So at that time, both photons are independent. They have both independent probability distribution functions. And if one is a zero ket, other can be anything. But in the entangled systems, if first one is a zero ket, second one is also zero ket. Or the opposite. It is possible to do the opposite also. If the property of the first is known, property of the second can be deduced. And now you can work out two qubit system of an entangled system. So here is what it is. There are states phi plus, phi minus, psi plus, and psi minus. I am saying the linear combination. I am assuming 0, 0 is one entangled state, 1, 1 is one entangled state, 0 is one entangled state, 1, 0 is another entangled state, 0, 1 is one. So that means I am taking them 0, 0 is an entangled state, 1, 1 is an entangled state, 0, 1 is an entangled state, and so on. So only these combinations are possible. If one is 0, 0, the other is 1, 1. You think of two qubit system, not single, two photon system. One is possibility is 0, 0 and 1, 1. First is 0, 0 combination, other is one combination. 1, 0, 0, 1 combination and 1, 0 combination. That means the first is 0 ket, the second is 1 ket, is known. So using all this, you can come out with these 4 states for the photon. 4 combinations only. Okay. Now I want to give you a small example of quantum communication link. So we consider transmitter as Alice. See, in the quantum world, people use this terminology. Alice is considered as a transmitter. Bob is considered as the receiver, and the Eve is the one who is trying to steal the information. So there are 2 channels. One is called a public channel, other is called a quantum channel. Public channel can be conventional one also, not necessarily a quantum channel. It can be a conventional fiber optic cable with classical information. Okay, we are worried about the quantum channel and its key protocols. So this is called BB84 protocol. I'll describe, and there are also other possibilities like high dimensional key distribution is possible. HDQKD it is called, and so on. Okay, and also people talk about device independent key distribution. You can work out a theory where it can represent any system. The possibilities are for any system. Generally, I would suggest you think in terms of very basic things. If you are thinking, you think in terms of coin tossing experiments. Then you think about the photon states, horizontal polarization and vertical polarization. Compare and then bring in the probability distribution function. That's how you can work out and understand all this quantum information technology. So I am describing just one simple protocol called BB84, one of the earliest protocol. And here you have this bulb is representing the quantum information source, and Bob, this is at Alice. And Alice has got two ways to represent the quantum information. So this is horizontal and vertical polarization. 0 ket is horizontal polarization, 1 ket is vertical polarization. Similarly, it is possible to use minus 45 degrees and plus 45 degrees. Minus 45 degrees can represent 0 ket, and plus 45 degrees can represent 1 ket at the same time. Okay, so if I get a qubit at the input, I can use the first mechanism or the second mechanism to represent the information. And in this protocol, Alice will use randomly either the first HV or minus 45 plus 45. Suppose first qubit comes, Alice will use this. Second one, the second one. Third one can be once again second one. Randomly by conventional, by let me say by a coin toss, Alice will randomly choose one of these. So if the qubits are coming, then what is the output we can work out? For example, 0 qubit comes and Alice uses the first HV basis. Then output is what is that? This horizontally polarized light. Okay. Suppose one qubit 1 is emitted by this, and Alice uses the second machine. Then plus 45 degrees is the outcome, like the first, second, third, fourth, fifth, sixth one. You see what you see here, first one and sixth one. These are plus 45 degrees. So you can work out all the combinations that Alice can emit. Okay. So this you can see here the bit sequence is given 1 1 0 0 0 1 0 0 1 0 1 0. So first qubit is represented by this plus minus with, because it is plus 1, it is plus 45 degrees. Second qubit 1 by using the first machine, that is vertical polarization. Then third qubit 0 by using the first machine, once again horizontal polarization. Like that, all these combinations are there. Now what does Bob do is the question. Bob has to recognize these polarizations. The idea here is Bob also will use the HV basis and 45 degrees basis. So the first qubit comes here. For example, well, once again you can go back from here only. First qubit is received by Bob in the HV basis, that is what is a plus. Second qubit is 1, is also Bob is receiving also by using the vertical basis. You see, Alice has done a different thing, but Bob has done a different thing. He is also using randomly. Bob also will choose that randomly and then decide what is the outcome. So when he chooses the positive basis, plus basis for the first qubit, then the output is 0. Then the second qubit is vertical polarization. He also uses vertical polarization and you get 1. Then he is using the horizontal basis. Alice is using horizontal basis for 0 and horizontal. This output is 1. For the next 0 qubit, Alice is using minus 45 degrees and Bob also using minus 45 degrees. This is cross. So see, all combinations are there here. Please work out carefully and you get this is the output 0 1 1 0 0 1 1 0 1 0 1 0. So this is different from what is transmitted. Okay, which are the wrong bits? Crossed ones are wrong bits. So 50% of the time you see that they are wrong. But Alice and Bob can do the full communication by using only the correct representation. That means what I want to say is only some combinations of Alice and Bob are going to work out correctly. We cannot exactly say Alice 0 horizontal, Bob 0 horizontal. Alice 1 vertical, Bob 1 vertical. Not like that. You can easily work out and observe. There are some combinations of Alice and Bob representation which are going to give you the correct representation. They can make a table and then work out using that. Okay, I hope you have understood. And what is the crux of the problem? 50% of the time they have to discard the bits. Okay, the table is not full. 50%. The table, the lookup table is 50% in this protocol. Okay, that is the main feature of the BBA. And if let me one more point I'll put here. If there is an Eve, I'll show you in the previous chart. There is an Eve here. If Eve is trying to steal the information, what she does is she knows that Alice and Bob are using BB84 protocol, so she will get 4 machines for HV and 2 machines for receiving and 2 machines for transmitting, and she will do exactly the same what Alice has done or Bob has done. So what happens? This lookup table will become bigger, double. Okay, lookup table will contain how many elements? Double the number of elements. And Bob and Alice doesn't know that someone is stealing the information. So what do? They have to compare their lookup table. If they compare their lookup table, they will find 25% of states are matching. The entries are matching only 25%. That means they will know that someone has stolen the information, has interpreted. That is the security provided by the BB84 protocol. Immediately, the transmitter and receiver will know that someone has interpreted the information. There are many other new protocols people have come out with, and like E92, E91, etc., which can become more efficient. Instead of only 50%, 90% efficiency, and so on and so forth, we can get it. At the compromise, there are a lot of other things. Like if there is noise in the system, what happens? What happens to the table? What is the quantum error rate? And also, you can also correct the information. If the information is wrong received, how to correct it? What is the mechanism that you can use? Quantum error correction, all these things are available now. People have worked out. A lot of theory is available on quantum information theory, but only thing that is not available is the physical representation. The devices are not there. Okay, technology is not there. That's an important problem in the quantum. That's why you don't have the quantum computers still. So people are waiting for technology to progress to build quantum computers. So now I would like to show you a few more pictures before we close. I have a lot of photonics in this, but we'll try to ignore. I have just put a few slides. The slides are available to you. You can work out. There's a good papers are there. I'll give you. You can go through them. So this is a quantum satellite communications picture. Then this is the idea of quantum internet. If you want to distribute quantum information across many users, there's a different problem because you cannot divide. You cannot split photons. And you basically you have to work with so many probability distribution functions. If there are 3 nodes A, B, C, you have to have one PDF for A, one PDF at B, one PDF at C. Not only one PDF, you have, because you are sending several qubits, you have to have a mechanism of this is the probability is distributed, you can say. In the quantum internet, the probability is distributed. The photon is at only one place, A or B or C. Earlier, if you have a power, 1 milliwatt of power, you can send half milliwatt to B and half milliwatt to C. That's not possible here in quantum internet. So a lot of work has already gone into this. A lot of mathematics also has gone into this. Very little bit, I'll tell you about the photonics before I go to the last slides. So photonics can be considered as the science involving light. Okay, like electrons. Electronics is the science and technology involving electrons. Okay, photons also are fundamental particles. So you can think of analog electronics, analog photonics, and so all those things. So in electronics, we use statistics. In semiconductor devices, use Fermi-Dirac statistics to represent all these semiconductor properties, band states, and so on. Similarly, use Bose-Einstein statistics for properties of dealing with photonic statistics. So there are a lot of information is there, a lot of things to come. Photonics is the technology which has penetrated into many areas. In particular, optical communication is a reality now. All the broadband communications and high-speed internet and all are possible just because of fiber optic communications. Okay. Then similarly, in the area of sensors, a lot of development is going on in the area of sensors. Optical sensors are very sensitive compared to electronic sensors also. Similarly, in future, photonics, you can think of photonics to play an important role in our technology. So what is necessary? Technological development is necessary. There's nothing like VLSI for photonics. Very small devices we have, modulators, switches, etc. In conventional VLSI, you have thousands, millions of transistors, memories, and so on the same chip. That is not possible in photonics right now. So technological development is necessary. Similarly, a lot of academic activity is going on. So there are a lot of academic activities going on. There are many universities and IITs and all these places where research on photonics and quantum is also going on. Okay? And also there are not a lot of national programs. There is a national quantum initiative now. There's also at national level also government and universities, they are taking up research programs in photonics. Presently in India, you don't find any courses. There's no BTech in photonics. Okay, but I suppose many of you know that there is a MTech in photonics in IIT Madras and other places also. They are bringing in advanced courses in photonics for those who are interested, those who want to develop, those who want to take up projects, those who want to do research. This is a very fertile area. A lot of scope is there in photonics. But of course, you need to work out the different mathematics. You see, the theory and the mathematical techniques in photonics are different compared to electronics. So I have some set of slides about photonic devices for quantum applications, like integrated photonics for quantum technology is this slide. We don't have much time to go through this, so I will skip all these photonics. In some other talk in future, we'll deal with quantum photonic devices. Okay. So we have devices, quantum communications, etc. Like typically, I just want to throw some keywords. You use gratings, Bragg reflectors, then couplers, ring resonators. Now all these things are the devices which can be used, which are used in the conventional photonics, like tunable filters, and you can make and so on. The same things can be used for quantum information functions. You have to work out the probability distribution functions. You have to work out the transfer functions, filter characteristics, and so on from quantum point of view. I would suggest someone please take a grating and find out what are the quantum properties. What is the quantum distribution? What is the spectrum, Bragg reflector spectrum or a filter spectrum of the device from a quantum point of view. Okay. So let me go to the last, towards the end of one of these slides. So people have also developed the entire BB84 protocol, QKD systems, and so on the tip, all on paper. Or on the optical table in the many labs all over the world, like in PRL. If you go to PRL Ahmedabad, they have got a lot of quantum optics experiments. In IISc, unfortunately, you don't have much. People are still working on theory. Okay, and in some other places also. In fact, I would say that many places people are simply working on preliminary type of work. So there's a lot more scope in that. Okay, so let me go to our lab work. In our lab, we have been working on quantum cryptography, then quantum random number generation we have done, then some algorithms we have worked out from quantum point of view, how they can be implemented using photonic devices and so on and so forth. 4 people have done PhD in our lab, and 1 or 2 people have done masters also, and so on. So these are some little bit. One slide I'll show you what our work. One of Mr. Rohit is on high dimensional QKD. Instead of using qubits, we do qubits. There are 4 states or 8 states: D1, D2, D3, D4. So you should look at ket D1, ket D2, ket D3, ket D4 for qubits, and you can work out all the what is the efficiency, how much information can be transmitted, and so on and so forth. You can also convert the protocols into HD versions. Okay, and you can also work out the angular momentum of photons to realize all these quantum gates, protocols, and so on. So these, you can see some of our papers that recently. One more slide. I just want to show you photonics a little bit. So in one of the ideas that we have in our lab is to use the modes of optical waveguides. What you are seeing on the top, see, one of our specialization in our lab is optical waveguides. You can build modulators, switches, branches, couplers, and all these things. You can do experiment also here. We can fabricate in that nano center. Okay, in IISC we have nanocenter where you can fabricate. I'm showing you a Y branch, top view of the Y branch. We can design it by using T0 mode and T1 mode, two modes. Instead of single mode, we design two mode waveguide. Okay, and I will represent T0 mode as 0 ket, T1 mode as 1 ket, and then work out all the properties of this Y branch. What is the outcome is, you see, the conventional Y branch means if you send 1 milliwatt of optical power, it will be half milliwatt at this point and half milliwatt at this point in the two output ports. If you are sending a single photon through this, represented by T0 mode and T1 mode ket states, then what you get at the output, if you observe, you get a 0 ket plus 1 ket combination. 0 ket minus 1 ket combination. That means this Y branch is working as a Hadamard gate. So that's how you can represent. You can realize Hadamard gate. You can implement Hadamard gate. Similarly, you can come out with the directional couplers, 4x4 switches to represent other gates. Okay. On the right hand side, I'm showing you a photonic band gap structure. Later on, in some other lecture, you will be learning. You may have come across now already quantum photonic band gap structures. They can be either holes or rods in the silicon wafer, and they have very good properties, including quantum operations you can do. You can make a Y branch with a quantum dots. That's one other thing that we have done. That's all I think. You can also implement BB84 protocol on the chip using higher dimensional. This is a BB84 representation using higher dimensional QKD. So this is a chart which shows how to generate qubits. You can use ring resonators and waveguides and so on to create single photon sources and all that. So that's all I have to say for today. Thank you very much for listening. These are some of the pictures which we take when some visitors come to our lab. And we have a good program on quantum also. Some of the students are working. Most of them that they are shown in these pictures are they are finished and left. One fellow is doing on quantum right now. So I hope you have enjoyed this talk. For further information, I hope you will go to the standard books. And if someone is interested to go deeper into this subject, I hope this program is also supported by the Photonics Society. I know there are many members who are members of IEEE Photonics Society. If you are a member of IEEE Photonics Society, you can get a lot of information about the quantum also. So please join and take up. If you are really interested in learning more and more deeper, it's a very good way. I suppose the organizers will motivate you into photonics further later on. So there are 5 journals in photonics, lightwave technology, photonics technology letters, etc. All you get along with the membership. Okay. So photonics membership will cost about $10 for both students as well as faculty. But of course, you have to be a regular member, and then you can join the photonics. At the same time, you can also join. So please take up. If you are interested, you are welcome to interact with us, our students. If someone wants to do a PhD in photonics, we can also give you some problem, or we'll identify someone who can help you. There are a lot of members in photonics in our photonics chapter in Bangalore. So they can, I hope some of you will be able to guide you also. One of the problems if you want to do in this subject is to find the guides. So that also we can help you. Everything based on your interest. If you are interested in quantum, photonics, etc., you are welcome. Thank you very much for listening. And I will once again thank the organizers for calling me to this program. I can take some questions.
Yes, sir. One question is because I started from beginning and ending. I was listening. So, like a Y branch, we can use for the representing the quantum state. So, whether directional coupler, which is a 4-port device, Y branch is a 3-port device.
Yeah, definitely yes. If you want to have a 2-qubit gate, 2 inputs and 2 outputs, you can use a directional coupler. See, this Y branch is a single qubit gate. So 1 qubit to the first port, 1 qubit to the second port, and then 3 and 4 outputs are there. So there should be 2 mode devices. There are a lot of ways to use directional coupler. Suppose you have 2 mode. Suppose in like what I showed, two input mode, two modes for the first waveguide, two modes for second waveguide, the interaction is more complicated. It's a matrix of 4 by 4, okay, not 2 by 2. So you can use it. You can use also single mode waveguide directional coupler also. First mode first waveguide one mode, second mode one waveguide, and you can also work out what is the function that this conventional directional coupler gives. Lot of
it
grating you
depends
can
on the
use.
application. It depends on the application
No,
also.
first of all, device is device. Application will come later. Okay, first is simply a device, directional coupler. You can use it as a power divider. You can use it as a mode converter. You can use it as a, whatever you want, switch, etc.
Coupler connector.
The other is the application. The directional coupler function is same, whether it is coupler, whether it is a switch, whatever it is. Okay.
Okay, sir.
Yes.
Thank you. Very nice. Thank you
Application
so much.
related also will be there. You may have to change according to the application, but the basic functionality will remain same. The mathematics is same. Similarly, grating also is a very useful device in photonics. So you can use grating also for all these quantum functions. Filters, for example, if you want to make a quantum low pass filter or high pass filter, you can use a grating. I have not shown, but you can also build neural networks. For example, I'll show you some pictures of our students. You are able to see this picture about our alumni Kalol Rice. Hello. Are you able to see the Kalol Rice? Let me go back. Yeah, these all are done.
Yes, sir.
On quantum algorithmic engineering with photonic ICs. Now he's in somewhere Georgia Institute of Technology. These are all his papers. Dynamical decoherence control. Then he has done some. I'll show you next follows. Bhavani's. Akshita has published very good papers on Europhysics letters, then physical reviews, and so on and so forth. Much above our present day IEEE journals also. Many people think that IEEE journals are at the top. So there are higher order journals like physical review. Nature is much higher. So she has published in Europhysics letters, physical review A, and so on and so forth. She has worked on many parts, but in general information processing, quantum information processing using cryptographic techniques she has done. She's a postdoc abroad. Bhavani has touched upon neural networks and so on using photonics, and also added quantum also. Both classical and quantum algorithms he has compared. Google PageRank, for example. Then recently Rohit has done. I have not put his work here. Okay, thank you very much.
So here, computer science people also can work.
Yeah, definitely. We need, see, one knowledge is not sufficient. So you can work from a computer science point of view also, but it is better to learn a little bit of physics. And of course, mathematics. Mathematics we cannot escape. Physics you can escape a little bit.
Okay, I will ask from audience because
please make a database of those who are interested in quantum, and then we can help them according to their requirements. Let them send one paragraph email to the organizers, and you please pass on that feedback to me. So in the future, we'll know. And also please participate in future lectures, and you also tell us what topics you want to be covered in our these lectures and FDPs and so on. Every time you need not listen to the same thing. Okay. We can, in your college, for example, if you want to conduct some quantum program or a photonics program in your college, we have IEEE Photonics Society. They can come and then take up the program. And also we have programs for the faculty specific. If not from students' point of view, some faculty are interested to do PhD or take up long-term research or projects, we can suggest what to do. Okay. Please be in touch. It all depends on your interest. If you simply listen like a story and go and take the certificate and go, there is no use. Okay. Thank you. Yeah, please.
Sir, yeah. Yes.
Sir, one question, sir. Actually, my name is Anand. Actually, I am a MTech passed student. Actually,
okay.
I'm interested in, sir, actually optical fiber communication, right? So
okay.
actually, I don't know much about the quantum computing, but I am
Okay.
interested in quantum communication. So my question
Okay.
is that how you look quantum communication with how you relate quantum communication with the current wireless communication and optical fiber communication. What are the advantage of quantum communication? How it
The
will
first
replace
advantage
fiber
that people
communication?
talk about is the security. It's a highly secure communication. Quantum, not only free space, fiber optic also. Quantum communication is considered as very, very secure. You cannot crack you cannot interpret the information. That is the first thing. Then I would suggest all those who are interested in quantum not to look at communication and computing separately. In your colleges, you have ECE department, computer science, etc. But actually, there is no distinction like that. Only for admission purpose, placement, you have divided for us, we have divided into these departments. In the actual physical situation, there is no distinction like that. If you work in a quantum communication company, if there is a company in quantum communication, you have to learn a little bit of physics also. You have to learn a little bit of quantum computer science also. Okay, you cannot say I will do only communication. I will not worry about quantum computing. They are all together. Don't worry, it's not very difficult.
Why?
Similarly, actually, even classical also is not difficult. If you are an ECE person, you can easily learn a little bit of basics of computers. It's not difficult. You should not look at them as a separate thing. Okay?
So one more question, sir. How you
Yes,
look
please.
the network devices which we are using currently in optical networks? So how many network devices will have to redesign?
For quantum network, you mean, is it not? You are talking about quantum internet like thing?
Yeah, quantum internet. Okay.
Quantum internet, you have to have a different devices. Presently, what people are doing is old devices, switches, modulators, routers, etc. They are working out how they behave for quantum internet. But in future, people have to devise new devices for quantum internet.
Every device is right?
Yes.
Can I get the the Chinese people that have done satellite communication?
Yeah, it is everywhere there. No, you type on the internet, you will get what is that. But they will not give all the details. Okay. They will, some secrecy is there, but particularly Chinese fellows, they will not give all the detail. In the publications, in the papers, in the conference also, they will separate some information. You have to work out yourself. You look at what they have done and you have to work out yourself.
Research that they have done in satellite communication. What is
Lab section.
See, the paper is there. They will give you mathematics and all that, but some important information will not be given.
Yes.
Actually, here in this meeting, Vaishali Dhare is there. I think Vaishali, you are there. Who is the next speaker?
What is the
Vaishali, you
topic?
are there?
What is the topic? Next topic?
Vaishali will tell. She has
Because
not
I
shared
can
the
listen.
topic. Quantum. Vaishali, you are there?
Is it quantum or?
Some disturbance. Hello, all of you, please. Hello, all of you, please mute yourself. Hello, all the audience. Kindly mute yourself.
The organizers can control, actually. You can mute everyone except who wants to speak.
Yeah.
Yeah, okay. Please ask the question. Yes.
Okay.
ये
Someone is asking.
कल करवाना है ना वो तो अब लोगों ने पहले करवा के जाना है पहले मैंने मेल देखो ना मैंने मेल में लिखा है
Some disturbance is there.
कितना है पूरा लेकर आए नहीं बीच के थोड़े
No, you can look at the audience list and you can control. There's no problem, of course.
चेक कर देती हूँ
Please
लेकिन
ask
ये
questions.
देखो मेरे मेल में लिखा है कल मैंने
Thank you, sir.
स्लॉट ही
So,
दिया है
Manjula, just kindly formal way.
मेल नहीं
I think no more question. So,
देख-
formal way you can wind up the session. Hello, Manjula.
डेट
Yes, ma'am, I am on the line. We'll wind up.
Yeah,
Ma'am.
yeah.
Good morning, sir. It's an honor to have Dr. Srinivas, sir, amongst us today. His wealth of knowledge, leadership, and commitment to excellence serve as an inspiration to us all. On behalf of the Oxford College of Engineering, let us extend our heartfelt gratitude for gracing this faculty development program with his presence and sharing his knowledge on qubits, multi-qubit systems, quantum gates, quantum computers, quantum communication, cryptography, photonics, and the future of quantum technology with us, sir. Thank you once again, sir. Thank you all for joining the session. Let us continue our learning journey again from 2 p.m. onwards.
Thank you.
Thank you, sir. Actually, you have given
Thank you,
from
thank
the
you.
beginning, so your talk was very interesting.
Yeah, I could
Thank
not
you.
use mathematics because that will take, see, if you use mathematics, you can explain exactly.
Yes, sir. Yes,
Mhm.
sir.
Okay, thank you.
Some other day we will see that. Thank
Okay,
you, sir. Thank you.
thank you.
Manjula ma'am, now for second session, kindly you give instruction. So people are
Okay.
disturbing actually. It's
We'll inform
very
Chenappa sir, ma'am. He's the organizer. We'll inform him to mute all the other participants while the speaker is on.
no no starting level, starting only you can mute. This option is there. In between you can't mute. So at the starting level before joining, only everybody should be muted. So me and organizer who is anchoring, only those two people should not be muted. Other all should be muted. Okay. So kindly you inform.
Okay, we'll inform sir.
Thank you.
Thank you.